Welcome back. The time has come to talk about linear equations of the form ax equals b. Linear equations. So I will start with a little bit of motivation. I will state the problem and then I will try to answer the question, why not just use computers? Why did we have to do all this introduction to make sense of linear equations as I promised you? What's wrong with just using a computer to get a solution? I'll try to convince you that using computers is an excellent idea, but at the same time, we shouldn't abuse computers. We should always understand what's happening and what to make of the solutions they give us, or what to make of the sometimes solutions, quote unquote, they give us, which are not exactly solutions. I'll explain in a moment. So this is what we're trying to do here, is that we're trying to solve this equation. X is an unknown, it's a vector. We're looking for x, if one exists at all. A is a matrix. It could be a linear map more generally, but I want you to think of it as a matrix. And B is a given vector. So we ask three questions. First of all, is there an x that satisfies this equation, or is this equation unsolvable? Second, if there is an x, is it unique, or are there more? There can be 2, 3, 4, infinitely many, I don't know. And the last one is, how can we determine the solution or solutions of such an equation? And let's move on to this question, which I believe you must be wondering, why not just use software to solve this linear system, this linear equation? And well, let's have a look. Let's try. Why not? Take this linear system, 1, 1, 1, 1, our old friend, times x is equal to 2, 2. And we can see that there is a solution here. 1, 1, if you put here 1, 1, it satisfies this equation. So clearly there is a solution. Let's give this problem to Python and see what it has to say. So I have copied this matrix A here. A is 1, 1, 1, 1. And my vector B is this one, 2, 2. I'm using NumPy, a famous linear algebra library, or module, as it is called in Python. And I'm saying that the solution, I want the solution of the linear system with matrix A and vector B. Let's see what Python has to say. It says singular matrix. Although there is a solution, Python cannot find it. So, right, okay, let's do what every engineer on the planet would do. Let's look it up on the internet. Let's go to Stack Overflow and see what the people there have to say. Second time is a charm. Let's try again. I want to solve now this linear system, not the same as before. I want to give you a different example. 1, 1, 1, 1 times x is equal to 1, 2 this time, a different vector. And I tried to solve it, and I'm getting a singular matrix error message from Python. And the guys here say, you shouldn't do that. You shouldn't use the command solve. Here it says the system equations you're trying to solve does not have a unique solution. linalg.solve cannot handle this. You may find that linalg.lstsq provides a usable solution. And let's now move on and do what almost every engineer on the planet would do. Let's copy and paste, of course, without reading the documentation. So here is the copied and pasted code. This is my matrix A. This is my vector B, 1, 2. And x is, I'm using the command lstsq with A and B. Now moving on, we find that this vector is the solution. What is the conclusion? We tried something, it didn't work. We went to Stack Overflow or somewhere on the internet. We found the solution. We copied the code without understanding what it does. We got an answer from the software. The conclusion is that we don't need mathematics, just computers. Not so fast, because this, what we found, is not really a solution. Why so? Because if it were a solution, this is my matrix A. Okay, this is my A here. And this is my vector B. If you claim you have found a solution, then of course AX minus B must be equal to 0. Otherwise it's not really a solution. So if I put this X into AX minus B, I'm not getting 0. What I'm getting is 0.5 minus 0.5. So this X here is not a solution. X is not a solution. So I think I have your attention now. We can start to discuss and try to make sense of linear systems. We will start with a simpler case, the case of AX equals 0. So I have 0 on the right hand side. This is a somewhat easier case to study. This type of linear system is called a homogeneous linear system. And the good news is that these systems always have a solution. Why? Because X equals 0 is a solution. There can be more solutions than this. Maybe we can find more x's that satisfy this equation. The set of all solutions, you know what the set of all solutions is the kernel of A. Of course it is the kernel of A. The kernel of A, as we defined it previously, is the set of all points x such that AX is equal to 0. And this equation here, this equation, has a single solution if and only if the kernel of A is equal to 0. And now this brings to memory a number of equivalent statements to the fact that the kernel of A is equal to 0, the kernel of A is equal to 0, the nullity of A is equal to 0, the rank of A is equal to n, the matrix is injective, the matrix is surjective. All these things are synonyms. The matrix is invertible. That's where I want us to end up. So the kernel of A is equal to just 0 happens if and only if A is invertible. This equation over here has a single unique solution if and only if, maybe it's worth writing it down. So AX equals 0 has a unique solution if and only if the kernel of A is equal to the trivial linear space, if and only if a number of things, one of which is that A is non-singular or invertible. Right, that's very interesting. So we just made sense of homogeneous systems, and this is in fact everything you need to know about homogeneous systems. Let's dig a little deeper and focus on fat matrices that have more columns than they have rows. They're like this, wide matrices. We know that the rank of A is less than or equal the smallest of the two dimensions. So since my matrix is like this, it is m by n. This is the smallest dimension. So the rank of my matrix is not larger than m. So from the rank nullity theorem, the nullity of my matrix, the nullity of A, which is equal to n minus the rank of A, the rank of A cannot be more than m. So this is at least n minus m. N minus m. And since n is big and m is small compared to n minus m is positive. Whoa, what does this mean? We said the nullity of A cannot be 0, it is positive. So this looks like perhaps a line, or a plane, or a three-dimensional space. The kernel, the kernel of A is either a line, or a plane, or a three-dimensional space, and so on. It is not trivial. There are quite some solutions. This system, AX equals 0, has solutions other than just 0. There are other x's which are not 0, that satisfy this equation, ax equals 0. How do we know? Because the kernel is non-trivial. How do we know that the kernel is big enough? It's not just a single point. The dimension of the kernel, the nullity of A, is somewhat big. It is at least 1 or more. So to put this all together, we have the system ax equals 0. The set of solutions of this equation is the kernel of A by definition. Number 2, we have a single solution, a unique solution, if and only if the kernel is trivial, if and only if the rank of A is equal to n, if and only if, as we said before, if and only if A is invertible, which can only happen if we have a square matrix, otherwise forget about it, it's not possible. Then if x naught is a solution, if you can find a point x naught which is a solution, then it's easy to observe that cx naught are also solutions. 2 times x naught, 5 times x naught, minus 20 times x naught, all of these are solutions. If you find a number of solutions, x1, x2, up to xp, I don't know, you find a number of points, all of which are solutions, then any linear combination of these are solutions. And lastly, if A is a fat matrix, then there is at least one non-trivial solution. So apart from 0, I will have another point, not 0, which satisfies Ax is equal to 0. This holds only for fat matrices. I cannot tell something like this for square matrices or for tall matrices. Now, how can we solve homogeneous systems using Python? So to solve a linear system, to solve a homogeneous system means to determine the kernel. So this is the question we should be asking, how to determine the kernel of A. And in Python we can determine a matrix n such that the kernel of A is the range of n. There is a command that gives you this matrix n, and then the kernel of A is the range of n. How can I use that? If you have determined this matrix n, you can observe the dimensions of this matrix. It will be n by something, r, let's say, and the rank of n will be equal to r, and the nullity of A will be equal to the same r. So once you get this matrix, just by looking at the dimensions it has, you say, how many columns does this matrix n have? 3, let's say. Okay, so what is the nullity of A? It is 3. Then second thing you can do with this matrix, take any z which is in r little r, okay, and take this vector n times z. This vector is inside the kernel of A. So if you're interested in taking one point, an element, if you're interested in taking an element of this matrix A, of this kernel, of the kernel of this matrix A, then do n times whatever. Take this matrix n, Python gives you this matrix, do n times whatever, and this will be inside the kernel of A. So that's very useful. And lastly, every point, let's call it t, inside the kernel of A can be written as n times z. So this n times z we're talking about here is a parameterization of the elements of the kernel of A. Any element of the kernel can be written like this. So we have just fully understood the kernel of A. Again, why the kernel of A? Because the kernel of A is exactly the set of solutions of Ax equals 0. And here is a specific example how to do this in Python. Say that you have this matrix. You have this matrix A. And you want to solve the linear system Ax equals 0 with this matrix A. Okay, you go to Python, you say n is equal to scipy.linalg.null space of A. It's a command anyway. I mean, I'm not teaching you Python now, so I don't want to spend too much time on explaining the commands. The thing is that there is a command that gives you this matrix n. What is this matrix n? It is this here on the right. How many columns does it have? It has 2 columns. So what is the nullity? What is the nullity of A? Exactly 2. The kernel of A is 2-dimensional. So now I want to take a point inside the kernel. So take a vector z, which is 2-dimensional. I'm choosing this vector absolutely arbitrarily. There is nothing specific about 1 and 3. You can put here absolutely whatever you like. 5 and 900, whatever you like. So take a vector z. For some reason, equals has disappeared from this slide. So z is equal to the vector 1, 3. Then do this, n times z. And then check what you get by doing a times t. You should get 0. Do it if you like as an experiment. Take this, put here whatever you like. This is arbitrary, whatever you like. Then do n times z and take this vector t. T is in the kernel of A. Congratulations, you have found a point inside the kernel of A. And then you can check, of course, that it is indeed inside the kernel of A. Do this, A times t, and check whether the result is equal to 0. How do we check? Have a look. How do we check? We determine the norm of A times t. I mean, A times t is a vector. You want to see whether this vector is 0 or anything else. This vector can be huge. It can have 1,000,000 elements. That's all right. Take the norm, which is just a number. If the norm is 0, then AT is equal to the 0 vector. Just a little note. Take this matrix. We can find that the kernel of A is spanned by this matrix n. So again, take this matrix, go to Python, find this matrix n. How many columns does it have? 2 columns. What is the nullity of A? 2, because this has 2 columns. Then t is inside the kernel of A, if and only if, and have a look at that. T, we know from before, is equal to n times, let's not call it z this time, let's be a little more creative, let's call it c from creative, n times c, where this c is in R2, okay? And this means that n times c, what really means is this. When you multiply a matrix n by a vector c, then the elements of c multiply the columns of n. So t is equal to c1 times this, the first column, plus c2 times this, the second column. So this is your characterization of the kernel of A. I'll write it here. The kernel of A is equal to the set of all linear combinations of the columns of n. So that's what matrix n gives me. Now, when it comes to non-homogeneous systems, we will use what we learned for homogeneous systems, and we will generalize to the case AX equals B, where B is not necessarily equal to 0. Let's have a look. We will try to solve the linear system AX equals B, and it is convenient to introduce this notation. Sol of A comma B is the set of solutions. It is the set of all x's such that AX is equal to B. This is the set of solutions, and we have 3 possibilities. One is that we have a unique solution. The solution of the system with matrix A and vector B is just a single point. The other possibility is that there are no solutions. In this case, we say that the system is inconsistent. We cannot solve it. And in this case, the set of solutions of the system with matrix A and vector B is empty. We don't have any solutions at all. And the third possibility is that we have infinitely many solutions. Then we say that this system is underdetermined, and we will examine these cases in what follows. So let's try to understand what happens a little geometrically. Say that we have the space Rn and the space Rm, and we have a matrix A, which is in R, M by N, but now I want to treat the matrix as a linear map from Rn to Rm that takes a point x and sends it all the way to A times x. So if you take this point x, let's say the matrix A sends it to Ax. If you take a different point x prime, it sends it to Ax prime. So again, takes this point x, sends it to Ax, another point x prime to another point Ax prime. And let's say actually that whatever points you take here, all of these, after the action of A, end up somewhere on this space, on the range of A. So this is what we mean actually when we say the range of A. It is all the possible values of A times x. Okay. So it is impossible actually to do Ax and end up here. You will not end up here. This is a forbidden zone. You can only do Ax and you will end up on this line. This is the range of A. This line. Take now a point B. You can take it wherever you like, but let's say that you take it on the line. If you take it on the line, then there is a point x naught that ends up here. You have solved the problem in that, if this is the case. You have solved the equation because Ax naught is equal to B. But to do that, you have to take B to be inside the range of A. If you take B outside the range of A, if you take B there is no point inside Rn that ends up here. As we said, all points, let me perhaps do it like this, all points go on this line. This whole set is mapped onto this line. This point B is outside the range. So there is no, I'll write it down. There is no point x naught in Rn such that Ax naught is equal to B. Why? Because this B is not inside the range of A. So the linear system Ax equals B has a solution, at least one. It may have more, if and only if B is inside the range of A. If and only if B is inside the range of A. And if the range of A is the whole Rm, that is, if the matrix is surjective, then, and only then, the rank of A is equal to M. And then there is certainly a solution. So if here we didn't have a line, if it wasn't just a single line, if the range wasn't a single line, if it was the whole space, then it doesn't matter where you take this point B, you always have a solution. So if the range of A is Rm, if the rank of A is equal to M, if A is surjective onto then you have a solution, certainly. You might have more, but you certainly have one solution. If the rank of A is smaller, if it is less than m, then there may be a solution, maybe there is no solution. We don't know. We have to check whether B is inside the range of A. And this condition, B is inside the range of A, is the same as saying that the rank of AB together, like you have the matrix A, and next to that you stick together the vector B. And you compute the rank of this new matrix A and B together. And if it happens that the rank of AB is equal to the rank of A, then we have a solution. So maybe the title of this equation is how to check whether there is a solution. Whether there is at least one solution. There might be more solutions, but I'm asking actually whether there is even a single one. For what I want to tell you now, I need to give you a definition first of all. It is a very simple definition. So say that V is a vector space and take a point V0, a little vector inside V. And let's say that U is a subspace of V. Let's do a little sketch. Let's say that this is my space V. Let's say that this is 0. I have the vector space, the subspace U. This is my subspace U. And let's say that I'm also taking a vector V, not inside V. Then we define V0 plus U. What does it mean? V0 plus U. It is the set of all V0 plus U where U is inside U. Let's try to make this clear. What is it really to say V0 plus U? It is this line. I have just translated my U. I have moved my U so that it runs through V. And this is my V0 plus U. So if you like, you can even forget about this equation. This is a geometric explanation. This is my U, this is my V0, the green vector, and this line is my V0 plus U. This is called an affine space. Affine space. And also when we say the dimension of this affine space, what we mean is the dimension of U. So the dimension of the affine space, when I say the dimension of the affine space, I want you to understand the dimension of this space U over here. And here is the result. That's an important result. This is actually the result we were looking for. Suppose that there is a solution, there is a particular solution, and we are asking, are there more solutions? So let's say I'm giving you a solution that I have found, let's say, using software. But software cannot give us infinitely many solutions. There are numerical methods that can give me one solution, an x0. I'm asking, are there any more? So there might be, and they're given by this formula. All the solutions of the linear system are given by a particular solution, which I may be able to get using software, plus the kernel of A. And this is an affine space. How is this an affine space? This is a particular point, this is a particular vector, and the kernel of A is, as we know, a subspace. Point plus vector space, point plus subspace. So the shape of the solutions of a linear system is an affine subspace. Another take-home message is, if I can find one solution, then I can find all of them. I just need to know the kernel. How can I know the kernel? I can do this in Python. How can I find a point, single point? I can do this in Python as well. And now using this formula, I can understand the geometry of all solutions. It is an affine space, as we said. Affine space. I'm missing an E. And I can have it there. I mean, I can determine it. And let's relate this to what we did before by computing a matrix N using Python. So take a matrix A. Take a matrix A. Go to Python. You want to determine the kernel of A. Python will give you a matrix N. How does it help you? How does this N help you to determine the kernel? Well, the kernel of A is the set of all N times Z, where Z is anything you like. Z is a vector of dimension R. R is the number of columns, of course, of N. So if N has 5 columns, the nullity of A is 5. If N has 1 column, then the nullity of A is 1. So N times whatever describes, parameterizes the vectors of the kernel. At the same time, go to Python once again and find an x naught, a single point, such that ax naught is equal to b. Solve the equation and find a single point if you can. And if you put this together with what we mentioned before in the previous slide, so x naught plus the kernel of A, you have this. I will write it with very big letters, x naught plus nz. This is how a solution, any solution of this system looks like. Plug in there whatever z you like and you'll get a solution. Change your z, you'll get another solution, and so on. So this is how you can solve linear systems fully. Not just to get one single point, but to get all possible points of a linear system. X naught plus nz. These are all the solutions. Just a moment. These points x are the points of the set of solutions. That's it. This is why we had to do all this introduction and talk about vectors and then matrices and then linear maps and the kernel and the range and the rank nullity theorem and so on, because now we can make sense of the solutions of a linear system. And you can see all three cases we talked about previously, the case of having no solutions, having infinitely many solutions, and having just one solution. You see it here in one equation. For example, what happens if we have only a single solution? Then you go to Python or to any software, you find your single solution. How do you know there are no other solutions? There is no matrix N. You will not find an N if the kernel of A is just one point. So these are, to put it differently, these R will be equal to 0, or to put it differently, in that case, the kernel will be equal to 0, or in that specific case, the rank of A will be equal to N. This can of course only happen if A is a square matrix. Again, a little summary. If A is a square matrix, there are two possibilities. The first one is the rank of A is N. What is the same? A is invertible, and there is a unique solution. And this unique solution actually is A minus 1 times B, although you're only allowed to use this formula on paper. This formula is to be used only on paper. Never, ever should you compute the inverse of a matrix. Unless you have to, it is absolutely rare. I doubt you will ever have to compute the inverse of a matrix using some software. Do not compute the inverse of a matrix using software and then multiply by B to find a solution. It is a very bad idea. It takes a long time on the computer, and it's likely that the result will be inaccurate. You don't want to do this. Instead, there are other special methods that you can give A and B, and they do their magic and they solve the linear system. It's not the point now. I don't want us to talk about this, how these methods work. you should not ever compute the inverse of a matrix unless you know what you're doing. But on paper it's fine. Then second, let's say that we denote the rank of A by R. Then there are two options. One is that B is not in the range of A, so there are no solutions, or B is in the range of A, and the set of solutions has dimension n minus r. I'm asking here, why is this the dimension of the set of solutions? But I will leave this to you to think about. It's not even a proper exercise, just think about it. Why is the dimension n minus r? And with that, we conclude the crash course on linear algebra. There are a few more slides here I've put together, namely on least squares, and later some slides on matrix factorizations. But this is the absolutely essential things I want you to know. And if you like, you can study the additional material by yourselves. Thank you very much for watching. Next time we will move on to optimization. That will be one step closer to doing optimal control theory. Thank you very much for watching these video lectures, and I'll see you in class. Goodbye.